Okay, great. Well, this is Berkeley time. Let's get started. Good afternoon or good evening, good morning to all of you from all over the world. Really excited to see you all here in EECS151 to 51A, Introduction to Digital Design and Integrated Circuits. I'm Sophia Shao. I'm an assistant professor here at the EECS department of UC Berkeley, and I will be the course instructor for this semester. I'm really excited. This is actually my second year at Berkeley. It's also my second time teaching this course. I really like the topic covered in this course, and I'm looking forward to working with all of you this semester. So a little bit about myself. I mentioned this is my second year here as an assistant professor at UC Berkeley. My research area is in computer architecture with a special focus on hardware design, especially domain-specific hardware architecture. I'm very interested in building efficient design with different kinds of hardware components and explore better ways to integrate them together for better efficiency. So before Berkeley, I spent a couple of years at NVIDIA, which is a graphic card company, and also very specialized in domain-specific computing. And I got my PhD at Harvard, also in the area of computer architecture. So I mentioned earlier, this is my favorite course. I still actually remember how excited I was when I was an undergrad and when I took digital logic design. It was an eye-opening experience for me, and I was really excited to see how the different components in either electrical engineering or computer science are finally connected in this course. So with that, I'm very excited for this semester. I'm looking forward to be working with all of you to explore this exciting topic or area together. At the same time, I also want to mention this is not a normal year. This is not a normal semester. I know many of you are facing very unique challenges, and we are still in a pandemic, and the different communities are also experiencing different challenges. There are fires going on, smoke, or also hurricane, and also different students may have your own different challenges for this semester. We are here to help. We have an amazing course staff. All of us are really excited about this topic, and we also want to share our excitement with all of you. So if you have any questions or have facing any challenges or really just want to share any of your concerns, feel free to reach out to us. We are always here, and we will try our best to help you in this semester, to help you really succeed, to learn the exciting topics that we are personally very passionate about, but also help you to deal with any challenges and difficulties that you might be facing in your daily life. So, well, this is the first lecture, and many of students have already asked whether the lectures will be recorded. So we will still be doing live lectures every Tuesday and Thursday, 3:30 to 5 p.m. Pacific. So I'm looking forward to interacting with all of you here during this slot. At the same time, the lectures will be recorded, and we'll also post the recording after the class. So if you cannot make the live lecture, you can always watch those recordings afterwards. All the lectures will be online, but we also have the Piazza channels, and you also have my email. So if you have any questions or comments, feel free to reach out me or course staff throughout the semester. So with that, let's get started. This is the first lecture of the semester. We'll give you a brief overview of the different components of the course and really share some of the ongoing research and also development in the area of digital design and integrated circuits. So let's get started. Let me see whether this works. Okay, great. So what are the goals of this class, or what this class is all about? Well, this class is an introduction class for digital circuit and digital design and integrated circuit. A core principle in this course is that this is an engineering course in the sense that we are really building things. And the design that we're building or the design principles that we are learning are very useful, not only just for this semester, for this course, but for your future endeavor as a hardware designers. I personally really like and really excited about the area about hardware design. It is an area where you can actually discover your own creativities. Different designs will have different constraints. Different designs will also have different challenges. And it is a job of the digital designers to actually figure out how to work around those challenges and how to solve those challenges creatively in their design process. So with this is really a hands-on course. We'll need to build things, design things, and that's actually a good way to actually discover your interest and your excitement about the topics covered in this course. And a very important principle that you will learn and will also cover a lot throughout this semester is a principle about abstraction. The design, especially today's design in either microprocessors or graphic card or even domain-specific processors, all of them are fairly complex. It is infeasible for any designers to actually understand all the different components, all the different corner cases of the design. A very important design principle in digital logic design is the idea about abstraction. We want to use abstraction to manage the design complexities and also use state-of-the-art tools and languages to help us manage and also understand different layers of abstraction. And those also will be very useful for you to analyze or characterize different behaviors of your design, including, of course, performance. We'll also talk about power and also cost. All the different metrics are super useful and also super important in today's design practice. And we need to have these kind of layers of abstractions to help us navigate the different design areas. Finally, I mentioned earlier, this course is a very hands-on course. We have lectures, but we also have a big lab components where during the lab, you will be able to actually apply the design principles we covered in the lecture in your own design practice. So you will learn throughout their semesters while debugging your own circuit or debugging your own design. There are many ways to get things wrong. And every year our TA is actually relearning or learning new things or new ways that you can actually get things wrong. So you really need to go through that process to debug your circuit and understand what actually went wrong, to learn how to actually get things right, how to have a functional and also performance circuit and design in the end. So this is a very important part of the course and also will keep you really busy throughout this semester. So we put this here last year, like design, digital design is not twitch.com. Well, this year I would say digital design is also not zoom.com, right? So of course we are interacting with each other on this Zoom platform, but so you will actually really get to apply those different topics we covered in lectures in your design practice. And that's a core component of this course. So with that, a little bit more about how this course fits into your design or your education curriculum. So as an EECS course, this course is a good example how we can actually bring electrical engineering and computer science together. Well, this course is for you if you have a more computer science background. You may have learned different programming languages, maybe even compilers or operating system before, but you are really curious about how you actually can run different programs eventually on today's microprocessor. Well, this course is also for you if you have a more electrical engineering or even physics background, where you learn different transistors or different types of devices, but are really curious how we can actually assemble different devices together to build larger scale system for different functionality. In particular, if you look at this kind of stack view of our EECS curriculum, EECS151 to 51A fits actually right in the middle. We'll cover different digital design principles, including fundamental about Boolean logic. We'll have a refresh there. We'll also cover combinational and sequential circuits and finite state machines. And on the circuit side, we'll also cover different combinational unit and also memory unit. And we'll also cover verification and different design tools, which are very practical in your future career as a hardware designers. So a little bit more about prerequisites. You may already see that when you enroll this course, we typically require at least like CS61C, where you actually learn C and Boolean logic before and have the first view of RISC-V ISA. Of course, I will also review those topics again in this semester to prepare you for your lab and design project. But 6.1, you can see this course as a natural next step as 6.1C, and the topics that you learned in your 6.1C will also be very useful in this course. And I mentioned this is also a EE. There's also a very strong component on the electrical engineering side. So topics you learned in EE16A or EE16B are also very important, especially on digital gates and RC network. Well, don't worry if you haven't taken like EE16B yet, or you haven't taken, or you forget some of the topics that were covered because it was many years ago. We'll also refresh some of the topics and to help you learn what are the more at the higher level, how the different gates and the components being assembled together. So those are the prerequisites, what you should learn or what you should at least cover before taking EECS151 and 251A. And another very related course to EECS151 and 251A is CS152, 252, Advanced Computer Architecture. In fact, some students, because CS152, 252 are always offered in the spring, so some of you may have already taken computer architecture before. So after you have taken 61C or E16A and B, you can do either. You can maybe take 152 first and then do 151 after, or do 151 first and then do 152 after. Both are fine. Both courses are basically the fundamental of modern computer architecture. And after those two, you can basically navigate any advanced grad level computer architecture course in the future. Is there any questions?
No.
Okay, let me try to mute. And for other co-hosts, if you can also mute participants who are not talking. So Tushar is asking, is there any graduate course you would recommend? And that's a very good question. So in fact, I'm actually teaching a grad level course, typically in the spring semester. So in this past spring, I taught EE292, Hardware for Machine Learning. It was still focused on the area of hardware architecture, but also bring in some of the advances in machine learning and think about how we can design specialized hardware for machine learning. So I remember some of the EECS151 students and also actually took 292 this past spring. So if you're interested, likely I will be offering another version of 292 hardware for machine learning, but with new, more advanced topics there. So if you're interested, feel free to also join us next spring for hardware for machine learning course. And to wrap up the discussion there on the circuit side, so 151 is more on the digital circuit and 140 actually covers the analog circuit design. So this will also prepare you really well for integrate if you're interested in careers in integrated circuits. So
before we move on, is there like a lot of demand right now for hardware for machine learning?
That's a good question, Prashant. So I would say definitely yes. So we'll cover a little more about the recent trends. So we'll get there in like 10, 20 minutes. But of course, I think architecture is always thinking about how we can make different applications run faster. And as machine learning become one of the most important applications these days, it definitely also get hardware designers really excited and try to think about what we need to do on that front. We'll cover more topics there. Very good question. Mm-hmm. So Michelle is asking, what's the relationship between this class and 105, if there is one? That's also a very good question. So we'll actually have a more detailed overviews about the course sequence at the Apple event in an hour. So you can take 102 either before, 105, either before 151, and it's actually recommended to take before 151 because 102 will give you a very good foundation about circuit design. But some students also take in parallel. In general, we also recommend students to take 105, but especially more recent years, we're not requiring students taking 105 before 151. But you can see those courses are either in parallel, or you can do 105 first and then do 151. You can also do after. They are related, but can also be done in parallel. But it's also a very important course in IC education. Any more questions? Okay, let's move on. So a quick refresher on 61C. Many of you, if you have taken 61C before, this may look very familiar. And the truth is that you will actually get more of this semester in 151, and it will be even more complex. If you enjoy this in 61C, you'll really like this semester, will really like this course. And don't need to worry, as I mentioned there, don't need to worry about details. We'll actually rebuild it and actually build a more complex version, but also instead of using fake tools, we're actually using state-of-art commercial tools in this in this design process to make it, to actually build a functional and performant design in the end. So at the end of 151, of course, we start from this 61C design, but towards the end, you will actually be able to build a complex digital system with different components here. So this is one of the examples that some of the grad students actually taped out a couple of years ago and published last year. This is one of the more recent Berkeley chips, which has, of course, a RISC-V core, but also have the Huacha, which is a vector unit, and also have different specialized functional unit and shared memory here, and also analog logic here for different functionalities. So this is really an initial step for you to show you how to do digital design, what are the different tools and description languages that you need to understand. And after that, once you learn those skills, you can actually apply this in your different design practice to build more complex and also interesting system on your own. So that's what we want to help you, what we want to enable you in this semester. And it should be a really fun experience there. So a little bit more on the logistics side, we talk about the different exciting area that we will cover in this course. And the most important thing to help you to achieve that is our amazing teaching staff. We have a really good team this year. And in fact, this is the first year we have 5 TAs. So we actually reach out to find resources and to find really good qualified students, both graduate students, master students, and undergrad students, to really help you, to work with you and enable you to build complex system on your own. I'm very excited to be working with all of them. As you may know, some of us actually already started working during the summer to get you prepared and started on the labs, and both FPGA lab and ASIC lab. So in today, we'll also do a very quick introduction to all the TAs here. So given the time constraint, we'll probably just every TA, every teaching staff, maybe say your name, which year are you, and what's your grad students, what's your research topic, your undergrad, what kind of topics or area that you're interested, and maybe just one sentence mention what's your favorite time of the day these days. So with that, let's get started. I'll just use the order here. So Harrison, do you want to start first?
Sure. Hi, everyone. I think some of you have met me from the ASIC lab yesterday, but I'm Harrison. I'm a third-year PhD student advised by Bora Nikolic. My research mostly centers around how to do like baseband processing with an eye for implementing physical design very efficiently. And I think my favorite time of day is probably morning because I'm on the East Coast, so I'm 3 hours ahead of you all, and my mornings are very free.
Great. Well, thanks, Harrison. Great to have you on board. Next, we have Jingyi.
Hi, everyone. My name is Jingyi. I'm a first-year PhD student advised by Bora Nikolic and Sophia Xiao. My research is mostly on computer architecture and accelerators. My favorite time of day is 6:30 when I wake up.
Wow, that's really early. Great. Next we have Junghan.
Hello, everyone. I'm Zhenghan Lin. I'm a third-year PhD student. I work with Professor Boran in college, and I'm in the same lab with Harrison. And so my research topic is I'm mainly working on RF circuits, and we're working on circuit generators. And my favorite time is the dinner time. So I typically cook my own dinner. Yeah, I'm really enjoying it.
That's great. Well, great to have you, Junghan. Next, we have Kareem.
Hello, I'm Kareem. I'm a fifth-year MS student advised by Professor Sophia. My research is mostly interested in hardware accelerators, and favorite time of day is probably just late night. I'm a bit of a night owl.
Okay, great to have you, Kareem. And next we have Charles.
Hello, I'm Charles. I'm a senior undergrad. I guess my favorite topics to study are, well, definitely computer architecture, pretty much anything related to, I guess, computing and hardware. And I guess my favorite time of the day is probably after dinner when I walk my dog.
Okay, well, that sounds fun. Great to
Yeah.
have you, Charles. So now you know our TAs and you also know when is their favorite time of the day. That's probably the best time for you to either bug them, post Piazza questions, and send them emails. Very likely to get very quick response during that time. So make notes. Again, well, I'm really excited to have all of them, and all of them have taken 151 to 51A before. And as you already seen, they are also very excited about the topic. So we have a great team and we are here to help you, and this should be a fun semester. So with that, a couple different components of the course. Let me see how to go. Okay. So some of you already asked earlier, so this is our course website. We'll post our lecture notes and also videos and also homework, labs and exams. And we also have links to some very interesting resources and also Piazzas. So bookmark this website. You will find all the useful information here with this link. This is EECS151. So Mark is asking, is that supposed to be FA20 in the link? That's a good, yes, I will update this. Yes, this should be FA20. Good catch. Yes. So Bo is asking, is anyone else's Zoom not changing slides? Can you still see my slides changing? Is everything? Okay. Great. So I just advanced to slide 12. So that's a, I'll also mention the slide number. So make sure that you see where are we. Great, so we're on slide 12 on class organization. I mentioned earlier, lectures are only a part of the class. We also have 2 discussion sessions. Harrison and Junghan will each lead one of the discussions. We have office hours with 6 of us as teaching staff. We have 6 hours per week. And we also have problem set and labs. We have both FPGA lab, ASIC lab, a little bit more about the labs in a minute. And a big part of the lab is the design project. And we'll also cover, well, discuss briefly about what we will do in midterms and the finals. So slide 13 on lectures, I mentioned like slides will be available on the website before the lecture. So Prashant asked whether we can do even the day before. We'll try to make that happen. Lectures will be recorded. I still strongly recommend if you can come to the live lecture. I'm really enjoying this kind of live discussion, and it's really good to see you all here. If you cannot make it, it's okay. We'll record the lectures. Make sure you watch the recording after lecture to actually get see what's going on this week. Even some of you may in different time zones make it very challenging to actually join the lectures on time. I would still recommend you to have some structure in your schedule, having a fixed slot where you will be actually watching either lecture videos or discussion videos so that you can actually still progress during the semester. Next, slide 14, so recommended textbooks. So there are no required textbooks this semester. We do recommend 2 textbooks here listed here, but most of the topics that we covered are self-contained on the slides, lecture slides, or even our discussion or lab. So those should be your single source of ground truth. But if you're really interested in this topic, feel free to actually take a look at those 2 lectures, 2 textbooks, and also the 3rd one. All of them are very useful. I really enjoy all of them, and I still actually go back to take a look at different chapters from time to time. So if you're interested, feel free to also take a look at those textbooks, but no textbooks are required this semester. So Jason is asking what topics does the 3rd textbook correspond to? The 3rd textbook is more on the BSI side. So this class is more covering both architecture and digital design, but the 3rd topic is focusing more on underlying CMOS technology and circuit design. It is still very useful if you're interested on the circuit side of the topic and even the device side. I will also recommend you to take a look at the 3rd textbook. So slide 15, discussions. So we'll have 2 discussions in this class, and Zhenghan and Harrison will each lead one of the discussion. Discussion will start next week. I also strongly recommend you to go to the discussion. We have 2 different slots. Hopefully at least one of them work for you. And if you can, we'll also record the discussions, but if you cannot be there, make sure you also watch the recordings after that. And the next slide 16. So we'll also have weekly homework throughout this semester. We typically will try to post the homework on Thursdays, and it will be due the next Friday. So you have roughly a week, a little bit more than a week to work on the homework. The homeworks are very important, I think, for you to actually understand the material. We'll cover different topics in lectures and discussions, but you also need to actually work on those homework, work on those problems to see how to actually apply the different topics that you learned in lectures and discussions into real world problem. And we will have 3 late days this semester in total. So if you have some constraint, you can now submit your homework on time. You have 3 late days throughout the semester. And after you use all the late days, we'll just get a 20% point deduction every day that you're late for homework. And we'll also post solutions the week after the homework. Labs, as I mentioned, that labs are very important. Many of you may already have heard from us communicating multiple rounds about FPGA labs or ASIC labs. Both are very important and very useful, where you get to learn the fundamentals of hardware description languages and how to use that in the digital design practice. Overall, you will have roughly 6 lab exercises plus a design project in the second half of the semester. All the labs will also be online and will also be recorded. As Harrison mentioned, we already had our first ASIC lab yesterday, and we're going to have our first FPGA lab tonight. So still try your best to attend the live lab where you actually get to interact with both your fellow students and also our teaching staff. We are very flexible in terms of different slots. So we have 3 FPGA lab slots and 2 ASIC lab slots, and at least one of the either FPGA or ASIC lab slots actually during the night. So for some students who are not in the US, hopefully that slot would at least work for you. Many of the students taking FPGA lab should have already received the FPGA boards. So we started the shipping process during the summer. Hopefully many of you have received that, and don't worry about it. Well, in the first lab, we'll actually get to test your FPGA board to see whether they function as expected. For the student who enrolled late, who haven't got their FPGA board yet, so here is a link for the FPGA board shipment. Fill out the form, and then we will ship an FPGA board to your preferred address. So that's on the lab front. Before I move on, any questions about the labs? Oh, actually, will there be lecture notes for each lecture? So Abhinav asking whether there will be lecture notes. The answer is no. So we will actually try to put all the content that we want to cover in the slides. So the slides and also in the discussion. So the slides should cover most of the should cover all the topics that will be useful for both your homeworks and also the midterm. So there will be no notes available besides the slides.
Do you think it would be enough to like go into depth into a topic to be able to solve problems?
So that's a good question. So we'll also do that in the discussion. So discussion is a good place where we actually go through problems and see how you can actually solve problem together with our TAs. And we'll also do that, some of that, try to do some of that during the lecture time. So Eric is asking, will this course use B-course or simply use website? We are not planning to use B-course unless there is a strong preference to use B-course from the students. We tend to keep everything open for this class, for this semester. So all the information should be available on the course website. If there is a strong preference to use B-course, let us know. Otherwise, we're not intending to use B-course. Dylan asked, do you do scheduled meetings with students? I only ask because I would love to ask you some career-related question. Come to my office hours, so we can, it's also on the course website and also post a Zoom link on the Piazza. So come to the office hour for that. Okay, let's move on. So next, we're on slide 18. So midterms and finals. So this semester we'll have 2 midterms and one final. All of the exams will be remotely proctored. We're still communicating with the campus on the detailed procedures, but we will communicate to all of you and with a written note on Piazza in the next week, in the next couple of weeks. But as of now, both 2 midterms and the final will be remotely proctored. For midterm, the final will also provide review sessions. Midterm, we are currently planning to do in-class midterm tentatively. We'll do 1 midterm in early October and another one in November. And the final slot is already finalized. So it will be Friday, the slot from, also you probably can also see in Cal Central. So that will be our final slot here. So one thing I want to mention that for midterms, we do midterms really to have a way to help you to split the loads in this semester and to actually help you to review the content that we have covered, and instead of cramming everything towards the end. So you look at our schedule, so we try to split the load up. So we have something covered in October and then do something in November. And then when we get to the final, hopefully you have already reviewed the important topics covered in the first half or 2/3 of the semester. And then you don't need to have a very heavy load towards the final. So Bo asked about Clobber policy. That's the next. So Jason also asked cumulative. What do you mean by cumulative? So if you're wondering whether we'll also cover topics that has been covered before, let's first talk about Clobber policy. Maybe that will be clear after that. So we're on slide 19 about Clobber policy. Yes, we do Clobber. Maybe you cannot make either one of the midterms, or if you take some midterms but don't think you did as well as you wanted, we will provide opportunities so that you can actually Clobber using the grades that you got in the final exam to Clobber the midterms. Do remember that you still need to do all the questions in the finals. So last year we also have a Clobber policy, and one student actually only did the final part, but they didn't do the first midterm session and also the second midterm session. So you still need to finish all the finals, but we will label which part of the final correspond to midterm 1 and which part of the final correspond to midterm 2. And if you do better for those midterm and for those parts of the final, we'll use that to Clobber the grades that you get in the midterm. So would there be alternative time slot for the midterms account for time zones? That's a good question. Currently, no, we're doing I'll mention later, we're doing our time zone survey. We'll try to find a slot for everyone, and hopefully this class slot, well, if you have very strong preference that you cannot make the class, the midterm slot, come to us, we'll talk to you. As of now, we are not planning to do alternative midterms and finals, but definitely come to us and we'll see what we can do to accommodate that. So Jason is asking the cumulative as the second exam doesn't dependent on the stuff. That's correct. So second midterm only cover the topics after the first midterm. So Tusha asking, can you clubber both? Yes, you can clubber both midterms. Great. Okay, so again, as I mentioned, all of this is trying to help you succeed. We don't have any particular one to make the exam super hard or super difficult to actually to make the class even harder. All of this is to spread the load so that you always have time to catch up and using those midterms as an opportunity to fill in the gap that you have in the semester. So slide 20, Piazza, we have already enrolled all of you, at least as long as you are actually enrolled in Cal Central, you should already be enrolled on Piazza. If not, join Piazza. We'll post all the important announcement and on the Piazza side. And if you have any questions, also feel free to post your questions here. Slide 21, well, hopefully I don't need to spend too much time on this. I already mentioned all of us are really excited about this topic and we really hope you enjoy the topics that will be covered in this course and we want to learn with you together. And there's no benefit to actually to either cheat or actually not doing your work and not actually learning with us together. So all of those policies are really designed to help you learn and also help us to actually facilitate your learning process. So let's learn together and there's no need to take the shortcut. We will learn together, we'll cover the important material and we will have fun. So just a quick slide 22, grading breakdown. For most of the students, you should be enrolled in both lecture, which is a 3-unit course, and also the lab. You can either choose the ASIC lab called LA or FPGA lab, LB. So both labs will be 2 units and the lecture will be 3 units. So for the lecture, the 3-unit course will do homework, as I mentioned, 2 midterms and the final, and this will be our grading breakdown. And then for ASIC labs and the FPGA lab will have both the lab component and also design component. Their homework drops and there are, okay. Well, feel free to answer the question directly. It's actually a little bit hard for me to keep track of all the questions on the Q&A. So if you can actually answer directly, that will also be very helpful. So next, slide 23. So as I mentioned earlier, so we'll cover those different lectures material, different topics in the lecture, but lecture, you really get to see the overview of the topic, right? You should actually spend time participating in the discussion and also spend time in homework. And also very importantly, in the labs, take the lab very seriously. That's actually a very important part of this lecture, of this course, where you actually see how the different design principles are being applied in the design process. So take the labs very seriously. You want to attend all the lab sessions, interact with TAs, and learn together with your peers, with your fellow students to see how you can apply those design principles together. So make sure you participate in the labs, take the lab very seriously. That's a very important part of the class. And slide 25. So Ryan is asking, do we get separate grades for the lab part and the lecture part? Yes, there will be separate, so it will be two separate courses. You'll get separate grades for the labs and the lectures. So final note, for this week, we'll have this pre-semester survey. Make sure you actually fill out the survey. We mentioned the time zone survey there. And labs have already started. So we have the first lab, ASIC lab yesterday, and we're going to have the first FPGA lab tonight. And the first homework will be released next Friday. And if you're not on PIASA yet, register PIASA as soon as possible. And during the lab, you will also need to get your class account here. So it's shown as yes, there will be 2 courses. And thanks, Kareem and Jing-Yi, for answering questions there. Okay, so those are the course logistics. So before we move on to the next part of the lecture, any more questions that you want to get answered right now? Okay, well, keep asking the question. If you have anything, feel free to post on the Zoom chat. I will try my best to keep an eye on the Zoom chat. I realize it's actually fairly confusing with this setup, but other TAs will also be there and help you answer questions there. So this class is about digital design and integrated circuit, and it's always fun. Actually, I really like the history part of the hardware design and also the integrated circuit design. It's really amazing to see how things have changed in the past 5 or 6 decades, and it's always fun to reveal where we start and where we are now and where we are going. So let's take a look at where we are now. So it's interesting to see, like, computer industry has changed very dramatically in the past 5 or 6 decades. When everything first started in the 60s or even in the 70s, we're talking about mainframe computing, scientific application. That's the core focus of the data processing. And nowadays, if you think about where we are now, we are using different types of digital system, different types of electronic system all over the place. We have our phones there. We're using the technology supported by today's semiconductor industry in all the different areas for healthcare, for education, a big area with the rise of machine learning to actually think about how we can apply machine learning to all the different principles. Some people also say, like, it's really interesting to see how the advances of machine learning is not only just in the application space, but also in the system and also in the architecture hardware space. Like Prashant asked earlier, how this drive of machine learning actually changed the hardware design. It is a really interesting thing to think about what we can do, not only just in the application space, but also in the hardware design space to make different applications still run very efficiently in modern or even in the future generation of hardware. I mentioned earlier, we are still in the very short history of computer architecture in the 5 or 6 decades. And many of you may know, actually a couple of years later, Hennessy and Patterson is also a faculty here at Berkeley, actually won the Turing Award on their contribution in hardware design and computer architecture. And in their Turing Award lecture, they mentioned that this generation, this decade, is really the golden age of computer architecture, where we are seeing exciting development in the hardware space, not only just for like mainframe computing or CPU or GPU. Different startups, different designers are building their favorite hardware for different applications in very creative ways. If we think about lessons from the last 5 decades of computer architecture, I mentioned earlier, there's always a drive in thinking about how applications, how the different software actually change the way we think about architecture, the way we think about different hardware innovation. And the interfaces, like we talk about the great idea of computer architecture and this notion of instruction set architecture. Over the year, we see this kind of tight negotiation between software and hardware to think about what's the right level of abstraction, how we should actually interact with each other to facilitate not only just the hardware design itself, but also make it easier to program for different applications and for different runtime systems. And finally, I think one thing really interesting about our field is that we are always very connected with the industry, because this is a very practical area. We're not daydreaming like weird ideas and to see how they, whether they are feasible or not. We always need to think about what's the implications of our innovation in this broader context of the semiconductor industry. And one thing really interesting is that there are always constant debates in hardware design. Which way should we go first? How we actually interact with different areas. And what's really interesting is that, of course, it is still a technical debate, but eventually, because our field is so tightly integrated in the industry, and a lot of this kind of technical debate can actually be experimented in the marketplace and see which technical principles or which design principles eventually win the market in the end. So I think that's really what's really exciting about this area, is that, of course, you get to think about the design principles, core ideas of different ways of building hardware, and you can actually test your idea in this industry to see whether that idea can fly or not. That's very unique about this industry and also this area. So with that, I mentioned like, okay, so here are we are actually talking about this exciting area, exciting opportunity that we can do to actually enable those innovation. Then how did we get here? Where did we start? We only have like very short 50, 30 year history, right? So what happened in this short history that actually enable us to be where we are? So it's hard to actually not to mention, and like transistors when we talk about integrated circuit, and it's also really in some sense surprising to see actually after all those years, like the entire, in some sense, like modern civilization, today's civilization also so dependent on the technology area, dependent on the technology area. We're relying like the networking, all the different applications, virtual interactions to actually interact with each other. But all of this actually starts like roughly at this point, 70 years ago, actually. First transistors start from Bell Lab, where we actually able to actually build the first transistor on our own and think about how we can actually generate current and switches using this fundamental technology. And actually not too far after that, roughly 8 to 10 years later, we actually, like this area actually come up with these ideas to not only building standalone component, we can actually integrate them together monolithically to actually build even more complex system. So one idea I mentioned earlier is about the idea of abstraction, right? So if you're from a more EE background, you think about individual transistors and how to actually understand the current and voltage relationship of different transistors. Well, after you have the first transistor, we are moving really fast to think about how we can actually integrate those transistors together to build more complex system. And then, both the first transistor and also the first integrated transistor actually won the Nobel Awards in physics. So that's actually so typically technology area is not that close to Nobel Awards. We take a look at Turing Award more closely, but this kind of initial innovation in the area of circuit design and hardware design, that's actually how everything gets started in the first place. So another thing you actually will hear people talk a lot, especially in the area of hardware design, is Moore's law. I used to joke with some of my colleagues is that it's very hard to actually sit through a computer architecture talk without any mentioning of Moore's law. It's just like how fundamental it is and how much actually people care about Moore's law in their daily job practice these days. So Moore's law is actually start from also at this point, like 50 years ago, if you look at the history of a little bit more than 5 decades, thinking about history of Moore's law, where it's actually a very simple prediction, right? So Gordon Moore really predict how the number of transistors will scale in the future microprocessor designs. As his first guess is actually roughly, how about every year? Every year, the number of transistors per chip will actually double every year. And then, of course, later there are several multiple modifications of what the exact delta should be for this prediction, start from 12 months, 1 year, and eventually these days when people think about Moore's law, it's typically the number of transistors should double every year. At the same time, Moore's law, if you really think about when it started, it actually, Gordon Moore made this prediction based on very simple observation. It's really hard to actually think how much people, if you look at how much people care about Moore's law and then think about how it actually gets started. Gordon Moore made his prediction by 4 or 5 data points, and it's very easy to extrapolate a line out of those data points to say, okay, how about if we continue this trend, the number of transistors will always follow this trend. And it's really interesting if you see, especially you look at the history of the before 2010, before 2000, people actually follow Moore's law very truthfully. If you think about the number of transistors, right? So it's about transistor scaling. And if you think about the number of transistors, it's actually roughly doubling every other year. And that's actually how we get bigger and faster processors, especially Intel processors, if you look at the history of the semiconductor industry. But as I mentioned earlier, when people think about Moore's law, we typically think about, okay, it is about the number of transistors will double every year. But if you actually read the Moore's law paper, it's not about transistors, but it's actually about cost. So what do I mean by that? So if you think about its transistor density, whether Moore's law whether Moore's law is alive or not, if you think about transistor density, basically the promise of doubling the transistors every other year. So that trend is actually, in some sense, roughly still continuous. So this is a presentation from Hot Chips last year, a former CTO of TSMC, which is a major semiconductor fabrication company. And they have actually characterized their transistor density or number of transistors per square millimeter, and to see actually the trends in the past roughly actually 5 decades, exactly 5 decades. In this way, actually, if you look at this transistor scaling trend, it's roughly still scales fine, right? We're seeing more transistors, of course, like memory and logic have slightly different patterns, but roughly over the years, we do see this kind of trend that the transistor density is still improving. Then why we are hearing so many different talks about, oh, the end of Moore's law, what we should do after the end of Moore's law? One thing, before we get there, even in our short history of this course, if you look at actually different projects, different boards that we use for this course, we also see actually we start from like this very simple breadboard, and then over the years we get to actually larger and larger FPGAs. And the most recent FPGA, the PIC-board that many of you hopefully have already got from our shipment, is actually pretty complex SoC, which have CPU there and have different FPGA logic there, and you can actually build a fairly complex design using this simple PIC-board at your disposal. So even our history of this course also follow this trend in some way in thinking about scaling. So our project complexity also growing over the year so that we can actually build more complex designs. But one thing I think what I was hinting earlier is that, of course, we see the transistor scaling, but at the same time, one thing that's actually missing in a lot of discussion in today's thinking about transistor scaling is a cost component. If you actually have time, I would strongly recommend you to actually read Gordon Moore's 1965, his original paper about Moore's law. And that's actually very fun. It's only 2 pages, very easy to read. And he actually mentioned about the observation he made and why he made this prediction about doubling transistor every year. Back then, his initial prediction. What he actually mentioned that the key reason to actually doubling the transistors, or the point where the transistor will be doubling, is actually this minimum cost point. So it's not only just we're doubling the transistors every year. we are also scaling the cost of our transistors, scaling the cost of every fabrication to reach this minimum cost component. So that's actually a very important component of Moore's law. It's not only just about density scaling, but it's also about cost scaling. So here, the one on the right, this is a fancy 3D graphics that other instructors actually put together. A very cool way actually to visualize how the cost of transistors actually also going down in the past, actually from mid-90s to actually early 2000. That's actually the golden age of Moore's law scaling. We actually see this kind of perfect cost scaling over that period where transistors indeed get cheaper. So we can actually still have a business model by putting more transistors, getting better performance in our semiconductor industry. But this is not true anymore. So you will look at more recent cost trends. So this is a presentation also from Hot Chips, which is a major semiconductor conference that happening every year. This presentation is from Lisa Su, who is the CEO of AMD, another major semiconductor company. So here, what this slide shows is actually, instead of looking at the older generational technology that we showed earlier before 2000, so you will look at actually more recent generation of technology, start from 45 nanometer technology all the way to more recent 5 nanometer technology. And then really looking at how the cost actually has scaled over the years. Interestingly, actually, the cost actually is not going down. They may be actually more or less flat, but still going up a little bit before 17 nanometer technology. But then you see this big jump actually from 17 nanometer to 7 nanometer technology. That's actually experienced a huge jump in terms of cost per transistor over there. And this is actually based on the TSMC. Again, I mentioned earlier, it's another major semiconductor fabrication company. And some of you may also be following the semiconductor trend and also news these days. And you may notice that roughly 17 nanometer is also where Intel got stuck in their semiconductor technology. So they have been stuck in 14 nanometer for a while, and they are moving to 10 nanometer, but this 14 to 10 nanometer move supposedly to only take like 2 years, but it actually takes much longer. In Intel term, it actually takes 5 years. So it's not only the cost is going up, it's not going down anymore, the cost is going up. It's also a lot harder actually to get better transistors these days. We need to put in a lot of resources, in a lot of research and development to see what we can do to keep pushing the semiconductor industry. So that's always, I think it makes sense for people to think about it's a density scaling, how many transistors we're getting, but also remember there is a strong cost component, and without this cost scaling, that's actually why it makes it harder for us to see more feasible technology scaling and also better performance scaling over the past few years. And this is TSMC data, and different fabrication foundries may also have their own data. So Jason is asking how many transistors are typically, in the ISA. We're getting to basically billions of transistors there. And you also actually hear about like Apple SoCs, even it's actually a mobile SoC, we are also in the range of billions of transistors these days. Actually, many years back, we're already in the range of billions of transistors. So it's really exciting time to think about the scaling and the technology at our disposal, but also understand the challenges there. So we're a little bit short on time, so I'm going to actually go, feel free to ask questions there. I'll try my best to cover those questions, but I will also make sure that we can get our topics covered in today's lecture. So another thing I want to quickly mention is that we mostly talk about the cost component of Moore's law and the transistor density. And another very important component when we think about digital design is how about performance and also how about power? How do they actually change over the 5 or 6 decades of the computer architecture, hardware design industry? So on that front, it's not only just Moore's law. Another term you actually heard a lot is what people call Denner scaling. So Denner scaling is from also in the 70s when Bob Denner at IBM think about how we actually, so you were thinking about we can get more transistors every other year following Moore's law, how we actually get better transistors, how we can actually use those transistors, use smaller transistors to actually get better performance and hopefully, and also better power efficiency. So then Bob Denner is actually the one to tell people how to actually design your transistors, how to build your transistors to follow Moore's law and to achieve the efficiency expectation from the Moore's law. Specifically, what Bob Denner specified is that once the transistor, the density gets better, means the transistor actually gets smaller, we can actually scale the device dimensions here by a fact that it will assume the scaling factor is K, so as shown in this table. So if we actually scale our device dimensions by a factor of K, we can actually scale voltage as well as current the same way by a factor of K. So in this way, we'll do actually go through the math that will be part of your homework to think about the delay component and also power density component. We can actually also scale delay proportionally also by a factor of K, but while maintaining the same power density. So that's actually a really important part of what people say the 5 decades of Moore's law. While Moore's law actually specify where we are going. It specifies that we're getting more transistors every year, but it is Denner scaling that actually tell us how we can get there. By following this kind of scaling rule to get faster, get better, smaller transistors, get faster transistors by getting a better delay, better frequency, but also maintaining the same power density. So that almost seems like a free dinner or free lunch for a lot of for our industry, meaning that you don't need to pay extra cost, but you are able to actually get better performance, get faster transistors with the same cost, with the same power density. But unfortunately, even we are talking about Moore's law, but it almost, people are actually also accepting the fact that Denner scaling doesn't exist anymore. So if we look at, we talk about how we scale down our transistor size to get better frequency in our hardware. And if you look at the past, again, before 2000, before early 2000, our computing industry actually roughly following this trend by getting smaller transistors and also getting faster transistors. And that's the time when we just wait for 2 years, you will get a faster CPU with higher frequency. So you look at the y-axis here is showing the frequency scaling. So by waiting for 2 years, you're getting faster transistors and you're also getting faster CPUs to actually get better performance. But because the end of Denner scaling, where even when you actually get better performance, get faster frequency, you cannot maintain the same power anymore. Because once you actually, we'll actually cover more in the lecture, in the later part of the lecture, but Denner scaling really dependent on the fact that your voltage will also scale with your transistor size, right? So when voltage scale with your transistor size, current scale with your transistor size, that's how you get better frequency. But what people are realizing that when you actually get to very small transistors, it's very hard to actually lower your voltage anymore. There is a minimum voltage that you need to maintain to make sure the transistor is still functioning. So roughly around early 2000, that's when we actually hit that voltage point, and in the sense that we cannot reduce our voltage anymore and we have to maintain the same voltage. Without a reduction of the voltage, the promise of Denner scaling is not applicable anymore. And that's the time when we see actually this multi-core transition in our industry. Instead of building high performance, high frequency cores, we're taking this multi-core approach to keep more or less the same frequency and the same performance per core, but by offering more cores to offer better performance. So that's a very interesting transition if you think about the implications of power and how that actually changed the trajectory of our industry. And the one final note here, so this is actually a very detailed study in actually capturing the generations of transistors in the past 5 decades from the starting of Denner scaling roughly in the mid-70s, and see how the transistor densities and also power have actually scaled over the years. So we still see, actually, if we look at the top of the curve, the red line here, which is the transistor scaling, we still see actually more transistors actually showing up every day, every year. But if you look at the middle part of the curve, when we look at frequency and power, we see this kind of plateau actually showing up in early 2000 or mid 2000, where we cannot increase frequency anymore, we cannot increase power anymore, as that's when we actually hit this bottleneck. And then as a result, very interesting, if you look at the end, the bottoms of the curve, where we actually see more cores showing up to actually still get better performance, but instead of actually having more powerful or higher frequency core, we are leveraging parallelism. We're using this multi-core based approach to get better performance. So I see a lot of questions here. Well, it's good that we have some discussion here. I'll think a little bit more how to better navigate the chats in the next lecture. But it's good to see a lot of discussion happening in the chat. And feel free to also ask questions to your fellow students and also to teaching staff during the lecture. So finally, one thing people think about the design of hardware. We talk about the different metrics here. We focus on the density metric from Moore's law, and then we get to talk about the power metric from the Denner scaling. But another very important metric in the design process is a cost component. Many of you may have already seen this picture before, where we're evaluating different costs, where the y-axis is a design cost of different generations of technologies across from the starting point, the 65 nanometer technology, all the way to the more recent 5 nanometer technology. What we see, definitely we see a big increase. As we mentioned, the technology becomes smaller. It takes a lot of effort to actually scale down to get to smaller transistors. At the same time, if you look at the breakdown of different cost components, one part of the cost definitely stands out, which is the software component, the purple part. It's really interesting to see, actually, we are talking about the hardware. This is still a hardware course, but as we're going through the different design part, software is very important in thinking about how you actually use this kind of more advanced hardware, especially more specialized hardware, not only just single core CPU anymore. We get to this multi-core region to actually have more leveraging more parallelism. And more recently, we get to this domain specific part to get more specialized accelerator. And all of those requires a different software effort to actually make full use of those transistors in the design process. At the same time, when we think about hardware, especially domain-specific hardware, it's not only just build a CPU and then you can duplicate for multi-core approach. You can always duplicate your CPU and then you get better performance. For every component, no matter whether you're doing architecture or verification or physical design or software, every component of the cost, you also need to tailor this cost for the specialized component you're building. So especially for, like, we talk about different specialized accelerator in the machine learning space, there's like TPU or also other flavors of hardware accelerator there. Think about all the different costs that we that show up on this stack need to be applied to those different flavors of hardware as well. And that will play a very important role in thinking about also understanding the cost for this kind of more specialized way to think about think about this kind of ways to think about specialized hardware. And that also motivates a lot of research going on here, both at Berkeley and also elsewhere, to think about what we can do to improve the design productivity, to make it easier to navigate not only the hardware design, but also software design, verification, physical design, to make it more feasible for designers, especially designers of smaller team, to actually build complex systems on their own. So when we talk about the design cost, I think one thing we mentioned in the very early on this course, one of the very important principles is the notion of abstraction, right? Instead of actually doing a very bottom-up approach where you take a look at all the individual transistors and think about how to actually combine all the transistors together to build a very complex function or very complex module. In this area, when we build hardware, no matter whether we're thinking about purely a digital circuit or digital and analog design, maybe also in different architecture area for either general purpose course or specialized course, we always leverage the principles of design abstractions. So of course you can do the hand layout to the very low level to think about how to actually build transistors, connect them together. But instead of thinking about everything at transistor level, throughout the course, what we will cover is how we can actually build layers of abstractions from transistors to build different gates, Boolean gates that we can use to assemble them together for a bigger functionality that we can build a complex microprocessor on our own. So, and more recently, I think not part of this course, we'll still use today's state-of-art commercial hardware description language in this course. But of course, when you actually go out, when you hear people thinking about different ways, even newer way, higher level of abstractions to think about hardware design, you will actually hear people thinking about either high-level synthesis. That's a very also interesting topic that people have been exploring for a while, in the sense that instead of learning a different language for hardware design, whether you can use the same language that people use to do software programming like C or C++, and take those languages directly and compile them to hardware. So that's also a very exciting and interesting area people are exploring to use alternative language to describe hardware. Another flavor of the hardware description language you may have heard of, especially at Berkeley, is this Chisel language, which is another higher level language that hides a lot of lower level details of Verilog or even system Verilog, but can enable you to build hardware very quickly and also efficiently. Either way, understanding these layers abstractions, understanding how we actually navigate different layer of abstraction will be very important in your future career to see how you can build not only individual components, but also assemble them together to build a bigger functionality. So with abstraction, the notion of abstraction, one thing you will see a lot is to have this kind of hierarchy in your design process. We talk about the individual transistors and how you actually get to build an inverter, build a circuit out of those transistors, and then build different types of gates, and eventually combining those gates into different modules that we will use in building a very complex processor that we will experiment in this design. And a lot of design principles that you will see here, you may actually find similar in even software engineering practice. So one thing really interesting is that to see how the different principles can be applied to different disciplines, but still have a very common root in the way we think about reducing the complexity. So when we get to the modular design, a lot of like software engineering approach, like divide and conquer, also show up. You want to decompose your large design into smaller components and think about how you can actually build individual components together, but also have a way to combine them in the end for a bigger and more complex functionality. Another very important part of using good principle in the design process is also thinking about not only design, but also debugging and also later for your verification. it's very challenging actually to debug a very complex design where you actually don't know which part of the design actually goes wrong. So you always build one unit together and have very detailed unit tests to see which part of the component, whether the design that you are designing, where the component that you're designing actually meets the specific functionalities, and see how you can actually debug and also verify this kind of individual component before you get to a super complex design that is actually very hard to navigate. So design abstractions, we'll talk about abstraction, very important, and following good design principles is also very important in typical design practice, but also very important in a course like 151 to 51A, where you get to experience different ways of building complex design. So finally, as a digital design course, we cover different principles of the trends of the semiconductor industry and different principles that can be applied in the design process. If you think about the core of digital design, it is in some sense, a very challenging problem where you have actually very specific design goals. You want to design for a particular for a different function, and also you're given particular metrics. Again, we talk about the performance metric, frequency metric, and power metric, and also cost metric, right? Whether you can reduce the cost of the designs. And given all the different constraints with all the different goals for your functionality and for your performance, you as a designer, your job is to think creatively what you can do to assemble different components together to design a functional hardware, meet different performance, cost, power metrics, but meet all those costs and also meet the functionality requirement. That's what we really want to do in this course. And we'll use your project and labs as example to help you navigate this space using those example designs with different functionality specifications and performance, cost, power requirement, and see what you can do, what kind of flexibility that you have to build different flavors of design to navigate this design process. So how do we learn how to do this? So in this class, we'll learn different primitives, the different building blocks that will be used in the design process. We'll also learn different, how to actually express your design, how to use a description language to express your design efficiently to build efficient design. We'll try our best to see whether we can actually have formal methods and tools to manipulate this representation, especially on the verification side. We'll have guest lectures from Apple in talking about some of the verification challenge, which is also very important in today's design practice. We'll see different examples and using modern CAD tools to actually build prototypes in both ASIC and FPGA. Again, all those labs and all the design projects are really a way to help you, to facilitate you to go through iteration of the design process with different goals, different functionality in mind, and see how you can actually translate those specifications, those functionality requirements and design constraints into a functional, performant digital design in the end. So one thing I mentioned earlier, this course is really a combination, it brings EE and CS together. One thing I really like this course is that this class is also, or the topic here, is also as a boundary between art and science. Of course, we'll learn how those two works, what are the different principles, how we can actually build things that follow the different specifications that we have in mind. At the same time, it also have a lot of flexibilities under your control, at your disposal as a designer. You need to think about what's your own design, what's your personal taste, and how you actually navigate the design process, thinking about different costs, different trade-offs, and what types of design that you like better to design, to actually put into hardware. So with that, you also have a lot of freedom, and it's really interesting to look at different design from different designers, and you will actually see different patterns in the final design. So, but at the same time, I mentioned earlier, metrics are very important in this design process. Of course, you can design your hardware in different fashion, follow different rules, follow different ways of thinking, but eventually we always have very objective measures to think about the quality of the design. As I mentioned earlier, performance, power, and cost, those three metrics are always very important, no matter whether you're doing your design for this class or in the future in your own career. You always need to think about, by making certain choice, making certain decisions in your design practice, how that would affect those metrics in your final design. So it is still, of course, a topic about creativity, but again, with certain constraints that actually tell you, and also very objective measures. So with that, this is the end of my lecture, the end of the first lecture, and this is also the last slide. It's really good to see you all and really experience this virtual learning experiment together. It's a very interesting area, a very exciting area, a lot of interesting research and development going on, and I'm looking forward to working with all of you this semester to explore this area together. With that, I'm going to stop the recording now, and next we'll have the Apple event, and feel free to participate after this. And I'll be also online for a couple more minutes if you have more questions, and also go through this long chat.